formulae. I told you the skeletal formula is where it just shows the skeleton of the outline of the carbons, does not show the carbons and the hydrogens attached to it, but just the outline of carbons. So we have the skeletal formula here. You have four carbons, so it would be 1, 2, 3, 4. Right here we have four carbons. In the second one as well. So this would be four carbons right here, and over here we have a double bond, so you put a double bond over here. Then we have four carbons, so you make this like this, and there's a double bond right here. Then we have four carbons over here. And then over here we have an OH. So you show it like this. This has four carbons. And then over here we have an OH. Then we have four carbons over here. And right here we have a Cl. Then we have four carbons over here. And right here we have a double bond O. We have four carbons over here. Right here we have a double bond O. Four carbons over here. And we have a double bond O here. Then this right here is an ester. So for the ester, it will be a carbon, another carbon with a double bond O, then a single bond O, then another carbon and another carbon. Then we have four carbons over here. And right here we have a double bond O with an OH. Clear? Is this clear? Do you guys understand how to write these skeletal formulae? All right, so let's now see the skeletal formulae for these organic compounds. Right here, we have five carbons in the main chain. 1 second, I will just move the name slightly to the right, left. Barely have space, 1 second. All right. So let's see the skeletal formulae for these. Number 2. So we have five carbons in the main chain. So this would be 1, 2, 3, 4, 5. Yes. So you have five carbons in the main chain. So you have 1, 2, 3, 4, and 5. Right here we have a double bond O. Don't show the H because the H is attached to the carbon. Then on this one you have a CH3 and a Br. So you will show the CH3 like this, just a stick, because this corner represents a carbon. And then it has one bond already. So the second, third, and fourth would be hydrogen. So you just draw a stick and you have what? Br. So you can show the Br like this, you can show it like this, you can show the CH3 at the top, at the bottom, whatever, like either way is fine. So CH3Br, then this would be a Cl, this would be a double bond, and that's it. That's what we have, the skeletal formula. Let's see this one. So you have five carbons. On the fourth one, you have a CH3 and an iodo. So you make CH3 and iodo. Then on the second one, you have a double bond O like this. Then here we have four carbons in the main chain. So I'm erasing this. These are four carbons. Right here you have a double bond. Right here we have a Cl, right? Then here we have a CH3. We have another Cl over here and a double bond O over here. Clear? Then we have this, number 5. This also has four carbons in the main chain. So let's show 4 carbons. Right here we will have double bond OOH. Then right here we have Cl, right here a Br. Then this will be a CH3 and a Cl. And this would be a double bond O with OH. Clear? Then this one also has 4 carbons in the main chain. So let's show the 4 carbons in the main chain. Then we have a double bond O here. We have a CH3 and an iodo here. We have a Cl over here. We have a double bond O over here. Then this right here also has 5 carbons in the main chain. Right here we have an OH. Then we have a Cl over here, an OH over here, double bond over here, and an OH over here. Clear? Is this clear? Do you guys understand this? All right, let's see. So the main chain has 5 carbons. So these are your 5 carbons. Yes. Right here you have a Cl. You have a CH3 here, a double bond here, an OH over here, an OH over here. Then this one has 1 carbon, 2, 3, 4, double bond O, single bond O, and another carbon. Then you have 1, 2, 3. This would be a Br. This would be a Cl and a CH3. And this would be a triple bond N. Clear? Then this has 4 carbons. 1, 2, 3, 4. Right here you have a double bond OOH. Right here you have a Br, double bond. You have a Cl over here. That's it. This has 5 carbons. So these are the 5 carbons. Now let's see. On the first one right here, we have an NH2. So you write NH2. These H's are with nitrogen. So you can write them. This has a CH3. There's a double bond here. This has a Br. That's it. Then we have number 13. Number 13 would be 4 carbons in the main chain. So you have 1, 2, 3, 4. Right here you have double bond OOH, acid. This is OH. This is Br. This would be a double bond right here. Again, 4 carbons in the main chain, 1, 2, 3, 4. Right here you have acid. You have OH and OH over here. Yes. Then number 15, you have 4 carbons in the main chain. Double bond OH. This would be a Br, a CH3. This would be an OH. This would be double bond OOH. Clear? Is this understood? Do you all get the skeletal formulae? Or to write the skeletal formulae for all of these compounds? Now, if you have methane, CH4, what will be the skeletal formula for that? So the skeletal formula for methane would be just a dot. Just a dot. Yeah, because this dot represents carbon. You can't draw a line. Line would represent two carbons. So this would be just a dot representing a carbon. Is this clear? What are isomers? We have two types of isomers. We have structural isomers and we have stereoisomers. So let's see isomerism. We have two types of isomers. We have structural isomers and we have what? Stereoisomers. So we have structural isomers and we have stereoisomers. Structural isomers are those where the molecular formula is the same. So these are isomers with the same molecular formula. So isomers with the same molecular formula, but different structural formula. So they have the same molecular formula, but different structural formula. There are three types of structural isomers. You have chain, positional. So you have chain isomers, you have positional isomers, and you have functional isomers. Right? What are stereoisomers? These are isomers with the same molecular formula. They have the same structural formula as well. So they have the same molecular formula. They have the same structural formula as well, but different arrangement in space. So they have different arrangement in space. There are two types of stereoisomers. You have geometric or cis-trans isomers. And there's a second type, which is optical isomers, also known as enantiomers. So we have structural isomerism and we have stereoisomerism. Structural is when we have the same molecular formula, but different structural formula. There are three types: chain, positional, and functional. Then we have stereoisomers. They have the same molecular formula, same structural formula, but different arrangement in space. Clear? Let's see structural isomers first. So let's see structural isomers. What are structural isomers? They have the same molecular formula, but different. They have the same molecular formula, but different structural formula. So let's see. Structural isomers. They have the same molecular formula, but different structural formula. There are three types. We have chain, positional, and functional. Now for this, you need to know your naming. You need to know your structural formulae. Let's see the first type, the first example, which is chain isomers. So let's see chain isomers. Let's take a chain of 4 carbons. Right here we have a 4-carbon chain, that is butane right here. So this right here is butane. Yes? So this is C4H10 butane, right? So you have C4H10, this is butane. Or if you want, let's add another carbon. Let's make it a pentane. So I can show you the chain isomers. So this right here is C5H12, and this is what? Pentane. Let's see the structural formula for this. The molecular formula is C5H12. Let's see the structural formula. The structural formula is CH3, CH2, 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 CH3. CH3, CH2, 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 CH3. Yes? Now, if you see the main chain here, the parent chain here is of how many carbons? The parent chain is 5 carbons. Now let's shorten the chain. Let's shorten the chain and make the main chain of 4 carbons. Main chain is of 4 carbons. Now the fifth carbon, do not put the fifth carbon on the first or the last carbon. Do not put it on the terminal carbons. So don't put the fifth one on the first and the last. You can put it in the middle of the molecule. So you can put it here. Now you'll be like, Miss, why not on the first and the last? If you put the fifth one over here, the main chain will again be 5. If you put it here, the main chain will again be 5. So you need to shorten the chain. So you will put the fifth one on, let's say, here, this carbon. So this will be a CH3 and you have all of this. Now, if you see, the main chain is of 4 carbons. It's of 4 carbons. This is still C5H12. And this is what? 2-methyl butane. Yes? And the main chain is of 4 carbons. Let's see the structural formula. That would be CH3, CH3, CH bracket CH3, CH2, CH3. Do you see the molecular formula is the same, but the structural formula is different, and is why they are what? Isomers. And which type of isomers are they? Do you see the structural formula is different because of the main chain? This one has a chain of 5, this one has a chain of 4. Therefore, it is a chain isomer. Now, let's further shorten the chain and make the chain of 3 carbons. Now, the fourth and the fifth cannot go on the first and the last carbon. So it will go here and here. So this is a CH3, a CH3. Yes, the main chain is now of 3 carbons. So this would be what? 2, 2 dimethyl propane. Yes, this is also C5H12 if you see. The main chain, however, is of 3 carbons. Let's see the structural formula. CH3, C bracket CH3 twice and another CH3. Or if you see, this carbon has 1, 2, 3, 4 CH3s around it. So you can write this as CH3, 4. Yes. So this right here is your structural formula. Again, you see, for all of these, the molecular formula is the same. But what is different? The structural formula. And why is it different? Because of the chain. Therefore, they are chain isomers of each other. Is this clear? Now, you don't have to write the structural formula and then check whether it's different to identify whether they are isomers or not. You can just name them. This is pentane, 2-methylbutane, 2,2-dimethyl propane. If the name is different, they are isomers of each other. Is this clear? Is this clear? Do you understand this? Now you can be like, Miss, we've drawn the CH3 in the second one. We've drawn the CH3 on this carbon. Can we not do it this way? 1, 2, 3, 4. Can we not draw the CH3 here? Can we not draw it on the third or technically the second carbon from the right? This and this is the same. Is why you need to know your naming properly. If you name this, this will also be what? 2-methyl butane, because now you will number from this side. Yeah. Here you were numbering from this side. So your alkyl gets the least number. So this is also 2-methyl butane. So both of these are the same. So it's not going to be counted as two separates. They will be the same. If the name is the same, it's the same thing. All right. So can we say C5H12 has three chain isomers? Is this clear? Is this clear? Do you understand the second type, which is positional isomers? Let's see positional isomers. Now, what is positional isomers? Let me take an example of C3H7OH. So you have 1, 2, 3. So you have the OH on the first carbon. So the main chain has how many carbons? 3. Let's name this. So this will be propan 1 all, because this is carbon 1, 2, 3. Let's write the structural formula. CH3, CH2, CH2, OH. Yeah. And this is C3H7OH. Yeah. Now, let's see another isomer for this. Now you got to change the position of the functional group. So the position here was on carbon number 1. Now you change the position of the functional group and put it on carbon number, let's say 2. Like this. So the main chain is still, you see how much? 3 carbons. So the chain does not change. The position of the functional group changes. And this becomes what? Propan 2 all. Wherever you number from, this is propan 2 all. Do you see the name is different? So they are isomers. And if you see, the structural formula will also be different. CH3, CH bracket OH, CH3. Is this clear? Now you'll be like, all right, miss, can we also have this as an isomer where the OH is on carbon number? Now you see, this is also technically what? Carbon number 1, because you need to give carbon the least number where you have the OH. So this and this is the same. Because when you name this, this will also be what? Propan 1 all. So it's the same. Is this clear? So you have, do you see right here? The molecular formula is the same. This is C3H7OH. This is also C3H7OH. Molecular formula is the same, but the structural formula is different. And why is that? Because of the position of the functional group. Here it's on carbon 1. Here it's on carbon number 2. So the position is different. Therefore, this would be what? Positional isomers of each other. Is this clear? So can I say in chain isomers, the structural formula is different because of the parent chain? Yes. So can I say that the structural formula is different? Can we say the structural formula is different because of the main chain? So structural formula is different because of the main chain or the parent chain. Yeah. Here, In positional isomer, the structural formula is different because of the position of the functional group. Yes. So they are what? Positional isomers. Now let's see the third type. We have functional isomers. So let's see the third type. We have functional isomers. Now, for functional isomers, we have a list. So we have aldehydes and ketones. They are always functional isomers of each other. Alkenes and cycloalkanes are functional isomers of each other. Alcohol and ether are functional isomers of each other, but you don't need to bother with this. Why? Because ether is not part of your syllabus. Then you have carboxylic acids and esters. They are always functional isomers of each other. Now let's see examples. Now here you see the molecular formula will be the same and the structural formula will be different because of the functional group. Do you see the functional groups are changing? So let's see examples. Let me take aldehyde and ketone first. So let's see an example of aldehyde and ketone. So let's see aldehyde and ketone. So you have 1, 2, 3, a 3-carbon aldehyde. Right here, main chain has how many carbons? 3. So you have a 3-carbon aldehyde. And this is what? Propan-1-al. Propanal. What is the structural formula? CH3, CH2, CHO. Yes. Now, aldehydes are always functional isomers with ketones. What's the molecular formula? C3H6O. Clear? Now let's make a ketone. Same number of carbons, same molecular formula. So a 3-carbon ketone, that would be this. Main chain has how many carbons? 3. 3 carbons. This would be what? Propan 2-one. This is CH3, CO, CH3. And this is C3H6O. Do you see the molecular formula is the same, but the structural formula is different? And why is the structural formula different? Because you've changed the functional group. So they are what? Functional isomers of each other. Structural, yes, but which type of structural? Functional. Because the functional group is different. Clear? So aldehydes will always have functional isomers with ketones. Let's now see the second example, alkenes and cycloalkanes. So let's see alkenes and cycloalkanes. So let me take an alkene, a 3-carbon alkene. This right here, let's name this. This is C3H6. You name this, this will be what? Prop1-ene. Let's write the structural formula. CH2 double bond CH, CH3. Yes, this is the structural formula. Now alkenes are functional isomers with cycloalkanes. So let's make a cycloalkane of 3 carbons. So you have a 3-carbon cycloalkane. That would be like this. Yes, if you see you have 3 carbons and you have 1, 2 bonds already, so the third and fourth would be hydrogen. This also has 2 bonds, so the third and fourth would be hydrogen. This has 2 bonds, third and fourth would be hydrogen. So you see this is also what? C3H6. You see the molecular formula is the same. What will be the name though? This will be cyclopropane. What will be the structural formula? CH2, how many times? Thrice. So CH2, CH2, CH2. Do you see molecular formula is the same? What is different? Structural formula. Therefore, they are what? Structural isomers, but which type? They are functional isomers of each other. Clear? Let's see carboxylic acids and esters. So let's see carboxylic acids and esters. Let's see the functional isomers here. Let me take a 4-carbon acid. So you have a 4-carbon acid, main chain 4 carbons. Yes, this is what? Butanoic acid. Yeah. And then we write the structural formula. It will be CH3, CH2, CH2, CO2H. Now, acids are functional isomers with esters. So let's make an ester with 4 carbons. So you can have any ester with 4 carbons where you can have 1 carbon of the acid and you can have 3 carbons of the alcohol, like this. Do you see all of this comes from the alcohol and is written first? So a 3-carbon alcohol will be what? Propyl. 1 carbon acid would be methanoate. Now let's see the structural formula. It will be HCO2, CH2, CH2, CH3. Then let's see this. A 2-carbon acid and a 2-carbon alcohol. This right here. So this would be what? Ethyl ethanoate. Yes, which is CH3, CO2, CH2, CH3. You have a 3-carbon acid and 1 carbon alcohol. This right here, this would be what? Methyl propanoate. So this is what? CH3, CH2, CO2, CH3. Do you see all of these they have the same molecular formula. They all have 4 carbons. They all have 5, 6, 7, 8 hydrogens and 2 oxygens. They all are C4H8O2. But they have different structural isomers, structural formula. Do you see? And therefore they become what? They are all functional isomers of each other. I mean, acid with esters, they are all functional isomers. So this, with this, with this, and with this, these are what? Functional isomers of each other, because the functional group is different. Whereas the esters, this one with this one and this one, the functional group is the same. This is also ester, this is also ester, this is also ester. What is different? The position of the esters. So these esters are what? Positional isomers of each other. Clear? Is this clear? Let's see a question. Draw all possible structural isomers. So draw all possible structural isomers of C6H14. Now let's see how you do that. When they say structural isomers, you have to include chain, positional, and functional. Now, if you see, this is alkane. How do we know that? The general formula is CnH2n plus 2. Do alkanes have functional isomers? No. I told you the list. Aldehyde ketone, acid ester, alcohol ether, which you don't have to worry about, and alkenes and cycloalkanes. So this won't have functional because it's an alkane. Yes? Now let's see. So you have the first one. You will make a straight chain 6-carbon alkane. I'm not putting the H's. So you have this Main chain, 6 carbons. This would be what? Hexane. Now you don't have to write the structural formula to see them that they are isomers or not. You can just name them. Just naming would let you know. Now you shorten the chain, and you shorten the chain by 1. Here it was 6. Now you shorten it, make it 5. The sixth one cannot go here, cannot go here. It can go where? On this carbon, let's say. When it goes here, what will be the name? It will be 2-methyl. How many carbons in the main chain? 5. So it will be 2-methyl pentane. Clear? You see the name is different. They will be isomers for sure. Now, you further need to shorten the chain, but you have other possibilities. You can now move the CH3 here. Yes. And this would be what? 3-methyl pentane. This is also an isomer. Yes. Then you have, now you'll be like, oh, miss, can I move it on the 4th carbon? Can I move it here? No, when you move it here, this is not 4-methyl pentane. This is the same thing as 2-methyl pentane, because then now you will number from this side. So this is the same as number 2. That's why your naming needs to be really proper in order to get isomers. So there's nothing like 4-methyl pentane. There's nothing called 4-methyl pentane. Now you further shorten the chain. Make a chain of 4. Now you got to put 2 more carbons, but you can't put them here. What you can do is you can put them both here. A CH3 here, a CH3 here. Main chain is now of 4 carbons, and this will be what? 2,2-dimethyl butane. Now you will be like, okay, can we make 3,3-dimethyl butane? No, 3,3-dimethyl butane will be the same thing as 2,2-dimethyl butane, because then you will number from the right side. You can, however, make this. What is this? This is 2,3-dimethyl butane. Clear? You can't make a 3,3-dimethyl. This is not a 3,3-dimethyl butane. This will be what? A 2,2-dimethyl butane. So this is not a separate isomer. Clear? Is this clear? Do you guys understand this? Do you have any other possibility? Now you'll be like, okay, miss, let's further shorten the chain to 3. And now we have to put 3 more carbons. You can't fit all 3 on this. You'll be like, okay, fine, let's fit 2 on here. And let's fit the 3rd here. I told you it can't go on terminals. When it goes on terminals, the main chain is now 4 carbons. It's a butane. Main chain is 4 carbons. On carbon number 2, you have 2 methyls. This is 2,2-dimethyl butane. Clear? Is this clear? So you have no other possibility here. And therefore, C6H14 will have how many structural isomers? 5. Do you see hexane and 2-methyl pentane? They are which type? Chain. Hexane with actually all of these. These are what? These are all chain isomers. Yes. Whereas number 2 and number 3, they are what? Positional isomers. Do you see that? Position is on carbon number 2. Here the position of CH3 is carbon number 3. Yes. Whereas number 3 and number 4, are both chain and positional. Do you see that? The chain is also changing and the position is also changing. Here the position was on carbon number 3. Here the position is on carbon number 2. Chain was 5, chain was 4. So they're chain plus position. You don't have to tell them separately. I'm just showing you so you can identify it. And 4 and 5 are what type? 4 and 5 are positional isomers because the chain for both of these is 4 carbons. So this is what positional isomers only. Here the position is on CH3 is on carbon number 2. Here it's on 2 and 3. Is this clear? Is this